we have been discussing different ways to measure links, okay, and so far we have seen sign networks, different ways to interpret sign networks, and so on. Now let's look at other perspectives. Again, let me repeat, these are more of a social science kind of perspectives which will try to quantify using network science theories, okay. So let's look at the interpersonal ties, okay, and we already mentioned about strong ties, weak ties, and ties which are absent, okay. So strong ties or strong edges are those edges which are generally developed among entities that share interest and beliefs. For example, strong ties between two friends, two individuals who are part of same college, for example. You can also thought of it as some sort of source of confidence or emotional dependency, right? Say strong ties are often built among individuals within a same family, okay, say between father and son, right, father and children, right. Whereas weak ties are generally developed between individuals who are not that connected, but they still share some commonalities, right. For example, say there are two individuals who go to the same college, right, but say after 10 years, right, they actually move to some other places. Friend 1 will move to say Australia, and friend 2 will say move to US, and after 10 years they may not be able to talk to each other quite frequently, but since they shared some common interest long times back, there is a tie between 1 and 2, right. These are kind of weak ties. So now, why do we need to quantify strong ties and weak ties? So there was a very famous experiment, again social science experiment, way back 1970s, 1971, during that time, by the famous anthropologist Mark Granovetter. Okay, so Mark Granovetter, what he did, he actually interviewed few individuals who recently moved, that time moved from one industry to another industry, one company to another company, and then so basically Granovetter asked that why did you move, okay, and where did you get the information from, right? Did you get the information about the new company from your close friend, from your family friend, or you got the information from somebody who you may not interact with quite frequently, okay? So he interviewed quite a few individuals who recently moved from one company to another company, and it turned out that most of this movement happened, right, because of friends who were not in their strong circles, right. Say for example, you are currently with TCS, Tata Consultancy Services, and you want to move, right, you want to move out, you want to move to another industry. What would you expect? Would you expect that your other colleagues from TCS would give you information about new openings, or you expect that colleagues who are outside TCS, for example your friends in Infosys, your friend in Wipro, right, they would give you opportunities in their companies, right, or they would give you opportunities in some other companies? You can easily expect that friends who are not part of TCS would be useful in this case, because they would give you they would give you opportunities about places which are which may be competitors of TCS, for example. Okay, so particularly from the recruitment's point of view, it is quite trivial to understand, or it is quite trivial to believe that this kind of referrals essentially come from friends who you do not interact with frequently, okay, and these friends are essentially your weak ties, your weak friends, right. Now if you think of different clusters in a network, right, so say let's say these are, I mean, each individual cluster you can think of as a closed community, and nodes interact within clusters very frequently, but there are links which connect two clusters, and these links are essentially weak links. Okay. So, if you want to really move from this cluster to this cluster, right, your weak links actually play an important role, okay, right, in terms of referral, in terms of better opportunity, better salary, and so on and so forth. I mean, it is not the case that your strong friends are jealous about you. That's why they are not giving you, they are not, I mean, they are reluctant to give you information. It's not the case. It happens because they do not know I mean, most of the times they may not know the other opportunities, right. So, those friends which are not close by, right, those friends which are part of other companies, they know the opportunities better than those who are part of the same community which you belong to, right. Now, this famous paper, this is one of the seminal papers in social science, network science, the strength of weak ties. I think it has got more than 4,000, 5,000 citations, I think, till date. In this paper, it was explained again from social science point of view that why weak ties are important, right. So, now how do we quantify the strength of a tie, strength of an edge? I mean, the simplest way to quantify the strength of an edge is you look at the neighborhood intersection of nodes, I mean, the neighborhood intersection of two endpoints of an edge, right. Let us say x and y, x is connected to some nodes, y is connected to some nodes, right, and if let us say both x and y share many common friends, therefore, it is highly likely that this edge, xy edge, is a strong tie. Whereas, there is an edge y and z, but none of this y and z share common friendships. Therefore, this might be a weak edge, right. So, the easy way to quantify it is to do some sort of intersection. So, intersection of neighborhood and union of neighborhood. So, this gamma x is a neighborhood set of x, neighborhood set of y, intersection and union. This is called Jaccard coefficient. Okay, Jaccard coefficient of the neighborhoods of x and y. All right. So, if you look at this example here, A, M and E, right. A has these friends B, C, D, E, B, C, D, M, M also has friends and so on. So, the intersection of A and M is 0, there is no common friend. Intersection of A and E is 1. So, and the union of these two things is basically 8 and 6 respectively. So, the neighborhood similarity of A and M is 0 and A and E is 1 by 6. Okay. So, you can say that okay, this is a weak tie, right. So, another similar concept is something called triadic closure. We have already discussed before. Triadic closure measures that okay, if x and y, say in this case, if A and B are connected and B and C are also connected, A and B are connected and A and C are also connected, what is the likelihood that B and C will also be connected in the future? Okay. So, the more the triadic closures you have in a graph, the higher the clustering coefficient. The clustering coefficient is a way of measuring the triadic closure. Now, let us try to understand different reasons behind the formation of this triadic closure. So, one reason is the opportunity, right. So, every mutual friend in this particular case, say mutual friend is A, right. So, every mutual friend like A between B and C gives, so A will give opportunities to both B and C to meet and become acquainted, right, with each other, thereby increasing the chance of developing a connection, more of an opportunity. Okay. So, let us say there is a referral system. Okay. So, A knows that B and C are good friends, but if you refer to B and C to become friend, A will get some incentive. Okay. I will discuss incentive in the later part. Okay. The next one is more of a trust. We discuss sign network. So in a network, if connections are formed based on some sort of mutual trust, okay, then X, right, in this case B and C, right, B is more likely to trust C. B is more likely to trust C because C has already trusted A and B also has already trusted A. So due to this balance theory, social status theory kind of theories, a trustworthy relationship can be formed between B and C. So the third reason is incentive. Okay, so let's say A has an incentive to bring its mutual friends B and C together in order to increase the interpersonal trust and cooperation among peers, right? Therefore, I mean this trust and cooperation would help A, right? Let's say A is a part of a company. Again, B and C also part of a company, and A is kind of a manager, and if A feels that I mean both B and C are reporting to A, right? But B and C are not talking to each other that frequently. So what A would do, A would try to convince B and C that, hey, why don't you talk? Why don't you talk to each other and start collaborating, and through the collaboration possibly the trust and the cooperation and trust will increase overall in the organization, and we will get some benefit. Okay, so these are the reasons. And how to quantify a triadic closure, we have already discussed. We can use clustering coefficient, local clustering coefficient, which is basically the actual number of edges among the neighbors divided by the possible number of edges among neighbors, right? So if you look at here in this example, say in case of node A has degree 1, 2, 3, 4, 5 and the clustering coefficient, and among them this edge this node, this node, this node, this node and this node. So this edge exists, this one also exists, this one exists, this one exists, right? That is all. There are 4 edges which exist. So and there are 5 nodes, so 5 C2 pairs and 4 pairs are connected, therefore the clustering coefficient is 0.4. Okay. So now let us look at another interesting social study. Now this is called Dunbar's number. Okay. What is Dunbar's number? So Dunbar in 1992 he tried to understand the relationship between the cognitive limit of an individual to remember the people or friends who the person interacts quite steadily, quite frequently. Okay. So let's say you have 2000 friends on Facebook, right? But you may not be able to remember each and every friend's activities, right? You may not be able to remember by name, in fact, all 2000 friends, right? And what Dunbar mentioned, Robin Dunbar mentioned, that our brain is capable of remembering only 150 close friends. Okay. So if you think of say encircling friends based on your cognitive ability, you will see that there are you can think of this kind of circles, right? This kind of circles where say there are only 5 friends who you interact very frequently. There are around 15 friends who you interact little bit less frequently. There are 25 friends who you interact even lesser frequently, and so on. And you see that there are in total there are 150 such friends which you can remember by name or by their activities. The remaining friends you may not be able to remember. Okay. And this Dunbar's number has a direct resemblance with the core periphery structure that we discussed in the earlier chapters, right? if you think of, if you focus on a particular node and look at the first core, right, first of neighbor, second of neighbors, third of neighbors, and so on and so forth, you see that after certain points, you know, the central node, right, which is the ego node, will not be able to remember more than 150 alters. Okay. So this was a very interesting study. And you know, you can also try to quantify edges based on something called bridge, local bridge, and so on. So basically, what is a bridge? A bridge is a tie or an edge between nodes that would otherwise be in disconnected components of the graph. Now, if we remove edge, if we remove the bridge, you would basically disconnect a network. Okay. So this is also related to weak ties, but you know, bridge is a very strong definition, right? So can we reduce the constant? Now, so you basically define something called local bridge. So a local bridge is basically a tie between two nodes whose deletion would increase the shortest path distance between two endpoints. Let's say in this case, right, say A and B. Now A and B are directly connected. If you remove this one, what would happen? The shortest path between A and B would be 1, 2, 3 and 4. So there is an increase of shortest path. Now what local bridge says? So on removal of a local bridge, the distance, the shortest path distance between two endpoints will be increased to a value strictly more than 2. Okay. So let's say there is a connection like this. There is a node here, right? Now if you remove this, what would happen? The distance between A and B is still 2. Earlier it was 1, now it is 2. So the increase is not more than 2. Therefore this is not a local bridge, right? Let's say there is a connection like this. If you remove this, what's the distance? Distance is 3. So 3 minus 1, it is 2. So still it is 2, right? Not strictly more than 2, but 2. 2 is okay. So what you are trying to understand? You are basically trying to understand whether there exist other mutual neighbors between A and B. Say in case of this kind of structure, right? So this is a mutual neighbor of A and B. And if you have a mutual neighbor, right, then there is no point in deleting it, because through the mutual neighbor they will be connected. Okay. So here you see that A and AM edge, this is a local bridge. All right. So how do we measure local bridge? There is something called edge embeddedness. Embeddedness is very simple, basically neighborhood intersection. You look at x's neighbors and y's neighbors, and if the intersection is 0, then it can be qualified as a local bridge, otherwise not. Okay. So what's the importance of a local bridge? Importance of a local bridge is that it basically indicates whether these two nodes are very close by, they receive new information, novel information, right, whether removing the bridge will disconnect it, right, and whether this bridge can act as a link which helps you, which helps the information move from one community to another community. Okay. So this was about local, bridge, Dunbar's number, and other aspects of link analysis. So we stop here, and in the next part we will discuss page rank and other quantifications of link. Thank you.